Pre-algebra lesson 117, equations with x squared, the Pythagorean theorem, or the Pythagorean theorem, depending on how you pronounce it, and then a demonstration of the Pythagorean theorem. The demonstration I'm not actually going to do in this video because it is very long and complex, but it is something you should read over on your own time. For this video, we're just going to focus on how to solve equations with x squared, how to solve equations with the Pythagorean theorem. This is actually a math lab. The demonstration is a math lab. It's not something that I think you could well, it's not something I could explain in less than 10 minutes. So let's go to equations with x squared. So if you remember Mr. Claiborne's rules for solving equations, we typically approach them using three fundamental rules, which one is we're going to use PEMDAS backwards, right, to figure out what numbers we're going to move. Now remember, these are solving steps. These don't include any rewriting we may have to do before we get to the solving part of the problem. Once we use PEMDAS backwards, we're going to use the whoops, I forgot to draw the arrow backwards. Use PEMDAS backwards. Then we're going to use the opposite action to solve. And then 3 is equivalent exchange. Whatever we do to one side, we'll do to the other. Right now, luckily, our initial equations with x squared, we'll be able to start right at these steps. They're not going to do any crazy things where we have to rewrite it just yet. So let's look at an example equation. Let's say we've got that x squared is equal to 9. Well, my goal in the equation, don't forget your goal, is to get the variable all by itself. Now, you may think, hey, the variable is all by itself. Wrong! No, there's a 2 right there. That 2 needs to go away. So, using PEMDAS backwards, there's no addition, subtraction, there's no multiplication, division, but there is an exponent, right? The exponent being x squared. So now, in order to get rid of that x squared, I have to use the opposite action of x squared, right? Now, if you remember during our order of operation problems, I taught you guys that square roots and exponents both count as the exponent step because square roots are the inverse operation of an exponent. So the opposite of x squared is the square root of x. So now I've used the opposite action. And last rule, equivalent exchange. If I do something to one side of an equal sign, I have to do it to the other. So I'm going to square root the right side of the equation. So now we solve. The square root of x squared is actually just x because the square root of any number squared is itself. And then what we have now is the square root of 9. The square root of 9 we should memorize. That's 3. Now, one last thing we're going to do, we're going to make sure we put a plus or minus 3 because of that difference of two squares theorem. I believe we talked about it already. Let me see here. Yeah, okay, I can't find out if we did it before. So the reason why I have this little plus or minus symbol, in case we haven't seen this yet, because I can't remember which class I've shown this to already, this little plus on top of a minus sign means plus or minus, meaning that the answer can be positive 3 or negative 3. Now, why can the answer be positive 3 or negative 3? Well, because the square root is just the same number times itself. So if I did the square root of 9 and I made it positive 3 times positive 3, well, I would get the answer of 9. So positive 3 works. Now, what if I did negative 3 times negative 3? Well, the negative times the negative would cancel itself out and make it positive. 3 times 3 would give me positive 9. So any positive square root has two answers, the plus or minus. We show that by putting this little plus or minus symbol in front of the answer. So just in case I haven't taught you that, that's what it means. If I did already teach you, then you're welcome for the free review. Now, what happens if we don't have a perfect square, right? What if I come across a weird problem like, let's say it says m squared is equal to, we'll say 51, okay? Wait, was that a bad example? Nope, that was a good one. All right. So if m squared is equal to 51, how in the world do I do this? Like, I know I need to do the square root of each side, but I don't know what the square root of 51 is. Well, it's actually a lot easier than you think. If there is no square root of 51, then we're just going to put plus or minus the square root of 51. That's it. That's our answer. We call it a day. So if you can't simplify your square roots, you leave it as is. Easy. Now, let's start talking about Pythagorean theorem. Now, the Pythagorean theorem, I'm pretty sure I've already talked to you guys about Pythagoras and how there are quite a number of historians who allege that he drowned one of his students. The Pythagorean theorem had to do with right triangles, so triangles with a right angle, and it had specifically to do with the relationship of the hypotenuse and the two legs, right? Forgot to mark these. This is a leg, and this is a leg of the right triangle. Okay, the hypotenuse being the longest side of the right triangle. Fun fact: you can always find the hypotenuse on every single right triangle ever by going to the 90-degree angle and drawing an arrow to it. That will work 100% of the time. If you draw an arrow to the opposite side of the right angle, that will always be the hypotenuse. Okay. Or vice versa, the two legs will always create the 90-degree angle. So if you think of it, the two legs will always be parts of the 90-degree angle. The hypotenuse will never touch the 90-degree angle. So you go to the 90-degree angle, you draw a line, kind of like if you picture a baseball field, it's like you're hitting a ball into the outfield, hit a ball into the hypotenuse, and you will always find the right triangle. It works no matter what orientation the right triangle's in. If it's this way, you just go to the 90-degree angle, draw an arrow to the hypotenuse. If it's this way, go to the 90-degree angle, draw an arrow to the hypotenuse. So it's pretty simple concept. Now let's talk about what the Pythagorean theorem says. So let's put some numbers on this this triangle. Let's say this length is 3. We'll say this length is 4, and the hypotenuse will be a length of 5. Yes, I chose those numbers on purpose. This is actually a really famous right triangle. It's the one most commonly used to explain the Pythagorean theorem. So what the Pythagorean theorem tells me, well, let's memorize it first. First, the Pythagorean theorem states that a squared plus b squared will always equal c squared. Now, what in the world does that mean? Well, parts of a right triangle, if you were to label the unknowns, the legs would be labeled as a and b, and the hypotenuse would always be labeled as c. Okay, now some of you may be wondering, well, does it matter if I get the legs out of order? No, it does not. You can reverse the letters on the legs. So this could become B, this could become A. It's not going to change your answer at all. What does matter is that C is always the hypotenuse. Okay? So with Pythagorean theorem, C is the hypotenuse. The formula is A squared plus B squared equals C squared. Now, I know your book has it written backwards. If you look at your book on page 368, it actually says C squared equals A squared plus B squared. It's the same thing. It's just backwards. It's okay. If I were to write the equation like this, it's still saying the same thing. It's okay. It's tomato, tomato. All right. Now, how in the world does this help us? Well, it helps us solve pieces of right triangles. So if I know two sides of a right triangle, I can find the third side using this theorem. So let's talk about what that means right here. We'll prove it with this one. So if I were to plug the numbers in, A and B, right? So A being 4, B being 3. So that would be 4 squared plus 3 squared, and then the hypotenuse being 5. So that should equal 5 squared. Does everyone see how I did that now? Instead of A, I put 4. Instead of B, I put 3. Instead of C, I put 5. It's just like our algebraic expression problems where we have to plug in the right numbers. So now let's solve this. 4 squared. Well, 4 times 4 is 16, plus 3 squared, which is 9, and that should equal 5 squared, which is 25. If I continue and I add 16 plus 9, well, that equals 25. And 25 does equal 25. That checks out. Now, this is true for every single right triangle ever. So let's do an example. We'll do 2 example problems, actually. I'm going to draw them down here. All right, so now we've got 2 practice problems here. I've drawn 2 right triangles with some missing pieces. Now, important thing I don't think I mentioned about the Pythagorean theorem is we have to logically understand that this is leg squared plus leg squared equals hypotenuse squared, okay? Some of you have been in the habit from arithmetic to memorizing position of numbers. So it'd be like, oh, first one plus the second one equals the third one. No, that's not how it works. We have to logically understand what parts of the triangle these are. So that comes into play a lot here, because if we look at this blue triangle and I go to the 90-degree angle and I draw an arrow to the hypotenuse, I see the hypotenuse is the missing number. Whereas if I look at this orange triangle, the hypotenuse is not the missing number. It's one of the legs that is missing, right? So we can see our missing numbers there. If they're different parts of the equation, that's going to change how I solve it. And we'll be able to see this as I solve these 2 examples. So let's start with the first one. What I have to do is I have to plug these numbers into a squared plus b squared equals c squared. I just drew the arrow identifying the hypotenuse, so I know that p squared is the hypotenuse. So something is going to equal p squared. That something is going to be this one squared plus that one squared. So a is 4, b is 5, right? It's the 2 legs. It doesn't matter what order I put them in. So now I just do 4 squared. Well, that's 16, plus 5 squared. That's 25. So 16 plus 25 equals p squared. This counts as the rewriting step of an equation. 16 plus 25, well, that's 35, 41. So now I have 41 equals p squared. Now I have an x squared equation that I need to solve, and remember I solved this by doing the opposite action of the exponent, which is the square root. Square root of p squared is just p. The square root of 41 is plus or minus square root of 41. Okay, now fun fact, since this is a geometry problem, it's not possible for me to have a negative length side on a polygon, so I don't have to do the plus or minus for right triangle answers. I can just say that p is equal to the square root of 41, and that would be my final answer. Okay, so we see that when the hypotenuse was missing, I had two whole numbers on one side, hypotenuse on the other. Now, if the leg is missing, that's going to change my equation. Some of you are going to be tempted to always put the missing number all by itself. That is wrong. Do not do it. We have to logically understand this. So start by going to your right triangle, drawing the arrow to the hypotenuse. Once I have the hypotenuse, I'm going to go ahead and write that down. So I'm going to have something is going to be equal to the hypotenuse squared. That's 9 this time. Now that something is going to be the 2 legs squared. So I'm going to have 7 squared plus m squared is going to equal 9 squared. So let's simplify this as much as we can. I can rewrite all these exponents. 7 times 7 is going to be 49 plus m squared equals 9 times 9, 81, well, just 81. Now I can go into my rules of solving. Now remember, I have to use PEMDAS backwards, and my goal is to get m all by itself. If I'm using PEMDAS backwards, I can't move the exponent first. I have to move this 49 first. Since that's a positive number, I'm going to move it through subtraction. So I'll subtract 49 from each side. That's going to cancel. I end up with m squared is now equal to 81 minus 49. Let's do some canceling. Borrow the 1. And I get m squared is equal to 32. Now I'm on the final step, which is to take the square root of each side. So now I've got m is equal to plus or minus root 32. But since it's a geometry problem, I'm finding the length of a side, I can just say that m is equal to positive root 32. And that is my final answer. Okay, that's it for Pythagorean theorem. That's all we've got for this lesson. Again, I do encourage you to take some time to look at page 369 and 370 in your textbooks. That's a very, very good proof as to why Pythagorean theorem works. If not, it's definitely something that we go over in Math Lab, especially as we get into Algebra 1 next year. If you have any questions, let me know on the school website, and I will see you in class.